Hello everyone, hope you're doing well these days and kind greetings from Spain. The paper I will now present deals with the improvement in batch loading resistance by using a triangular cell in the design of launched steel bridges. So, this paper really deals with a well-known issue, which is that when launching bridges, a critical aspect is to control the introduction of the reaction from the bearings directly onto the web as the bridge is erected. Since vertical stiffeners are equally spaced along the deck, it's obvious that the reaction from the launching pad will be eventually applied directly onto the unstiffened web panel. And this type of loading is controlled by the known as patch loading ultimate limit state. So therefore, it is very important to assess as accurately as possible the reaction, the resistance to patch loading, because the whole design of the bridge, that is the web thickness or the spacing between transverse stiffeners, may fully depend on the design phase. There are several ways of improving patch loading resistance, but one is placing longitudinal stiffeners on the web. But no doubt that a much more effective and without doubt economical solution is placing no longitudinal stiffening on the web and instead using a triangular cell connected to the bottom flange, which receives directly reaction from the launching pad and helps the web to resist patch loading. Here you can see such a design with the bottom triangular cell. So, how can a triangular cell improve patch loading resistance? Well, basically, in a simple eye girder, reaction from the launching pad is applied directly onto the web and balanced with vertical in-plane compressions applied along an effective web length, which is basically the length of the launching pad. When you include a bottom triangular cell, what you have is truly a beam-like member whose stiffness is capable of distributing the applied load along a much larger, much longer effective web length. But not only this. The second aspect, important aspect, is that in the eye girder, the applied load is fully balanced with the vertical compressions on the web. The integration of the vertical compressions gives the 100% applied load. But in the case of the bottom cell, the vertical compressions on the web balance only 84% of the applied load. The rest, 16%, are shear forces acting on the bottom member. Shear forces which are transmitted directly onto the vertical stiffeners by the bottom member in bending, and therefore never loading the web and helping it to resist patch loading. We can clearly see the contribution of this beam-like member, this bottom cell, with the aid of a hybrid finite element model, in which the web is modeled with shell elements and the bottom member is modeled with beam elements, which helps us to obtain member forces on this bottom member. We can obtain bending moments and shear forces on the bottom beam-like member. What we can see from these graphs is that when vertical stiffeners are placed wide apart, Resistance to patch loading is basically a local resisting mechanism in which the applied load is resisted by vertical compressions on the web, with very little contribution from the vertical stiffeners, as you can see here in the small gap in the shear forces of the bottom member, which at the transverse stiffeners gap in the shear forces, which is equal to the force transmitted to the vertical stiffener. When you close up the vertical stiffeners, well, their contribution increases because the bottom beam-like member, its stiffness, is capable of transmitting a larger fraction of the force directly onto the stiffener. But finally, if you close the stiffeners as much as to be closer than the effective web length, what we can see is that compressions get constrained between the stiffeners. The effective web length is reduced to the spacing of the stiffeners, but in exchange, the vertical stiffeners received a great fraction of the applied load, as we can see here from the large gap in the shear force of the bottom beam member. So, what we can state is that patch loading is the sum of two contributing factors. The first one is the contribution of the web to resistance, which is the contribution of the web by means of the vertical in-plane compressions which balance part of the applied load. But the second factor is the contribution of vertical stiffeners, contribution which may be contributed in two different ways. The first one is when vertical stiffeners are placed wider than the effective web length. In this case, their contribution comes from the bottom beam member, flexural resistance of the bottom beam member, which is capable of spanning the web and transmitting part of the applied force directly to the stiffeners. And the second way of the vertical stiffeners contributing to resistance is their direct contribution to resistance when they are placed closer than the effective web length. In this case, they manage to constrain the effective web length, they constrain the resisting web between the stiffeners, but in exchange they receive a large fraction of the force directly from the bottom cell beam-like member. So, well, up to here, these are more or less the ideas I presented in the Steelbridge Congress held in Millau in 2004. So 17 years and a pandemic disease later, what I've managed to do is to improve the current Eurocode patch loading formulation to consider the contribution of vertical stiffeners. Because as you can see in these graphs, if we plot resistance calculated with a nonlinear finite element model against the mechanical slenderness, in the case of a simple eye girder, the obtained results with the finite element model, well, they are accurately estimated by the current Eurocode formulation. But in the case of a girder with a bottom cell beam-like stiff member, what we observe is that accuracy is not as good in the case of more stocky webs, but most significantly, the current formulation clearly underestimates resistance in the case that stiffeners are placed closer than the effective web length. So we can say that the current formulation, when applied to the case of a beam with a bottom cell, correctly assesses web contribution to resistance, but clearly fails to account for the second factor of resistance, which is the contribution of vertical stiffeners to patch loading resistance. So, dealing now with the improved formulation, I will not go in detail with this formulation because it's a bit too messy, especially for a recorded presentation, but I will give the basic ideas. And these basic ideas are that when stiffeners are placed closer than the effective web length, we can evaluate, we can assess their contribution to resistance by means of a 4-hinge plastic collapse model, which is the same model as the one used for the current Eurocode formulation, except that we include the plastic contribution of vertical stiffeners to resistance. Operating with this model, with the adequate mathematical operations, what we obtain is an expression for the effective web length, which is a function that depends on the stiffness of the stiffener, and it is a decreasing function. As the stiffener gets more stocky, gets stiffer, the effective web length is lower, is reduced until it's limited to the spacing of the vertical stiffeners. But despite effective web length gets lower, decreases, the total resistance is not a decreasing but an increasing function, in contrast to what happens with the current Eurocode formulation. And this is thanks to the consideration to accounting for the contribution of vertical stiffeners to the plastic resistance. In the end, what we obtain is a formulation which is formally identical to the current Eurocode formulation, except that plastic resistance takes into account contribution of vertical stiffeners. So we have obtained a new improved formulation which solves the problem of inaccuracy, of underestimation of the current formulation when stiffeners are placed so close together that they interact with the effective web length. We have also obtained an expression for the other case when stiffeners are placed wider apart than the effective web length. And this model is a very simple Winkler beam model in which the vertical modulus takes into account the in-plane stiffness of the web reduced by the resistance function to take into account web buckling. Very simple model with that we can use to obtain the fraction of the applied force which is transmitted to the vertical stiffeners by the bottom beam member in bending, spanning the web between the vertical stiffeners. And finally, just to conclude, this is not just a theoretical formulation. It's an improved formulation which can be used to design bridges, because if we take off all longitudinal stiffeners in the cross-section of the Sava bridge, which I showed at the beginning of this presentation. If we take off all longitudinal stiffeners, what we obtain is that patch loading reaction of the unstiffened web panel is less than the applied reaction during launching. So we have to solve that problem, and we can try to increase the launching pad length, but still we cannot obtain a resistance, sufficient resistance, much greater than the required reaction. We can also try to reduce spacing of the vertical stiffeners, reduce the spacing from 4 to 3 to 2 meters, but that still is not enough. Still, a vertical patch loading resistance is lower than the applied reaction. So we only have one solution, only one, which is to increase web thickness from 22 to 24 to 26 millimeters all over the deck length. And in this case, we finally obtain 5,000 kilonewtons patch loading resistance greater than the reaction on the launching pads, design reaction on the launching pads. But what happens if we change the design and we use unstiffened web panels, but we include a bottom triangular cell? When we use that design and we use the improved formulation to assess patch loading resistance, what we obtain is that resistance increases over to 8,000 kilonewtons, approximately twice the required patch loading resistance. So the bottom cell is really very, very effective in increasing patch loading resistance. But not only that, also with a bottom triangular cell, collapse shows a large ductile plateau instead of the brittle, fragile collapse mechanism of the simple eye girder without the bottom beam-like stiff member. So, just to finish and to give a final idea, when we want to improve patch loading resistance, we may use a bottom cell, and what we have to do is to strengthen the cell, not the web, as the most effective way of improving patch loading resistance. So thank you very much for your attention, and bye-bye.